Alrighty, so the last time we met, I derived for you these equations in pink that we use a lot in acid-base chemistry calculations for pH, pOH. They all stem from the self-ionization of water, which is basically the equilibrium expression. No different from what we studied in the previous chapter. And even though, for the most part, water stays as liquid water, a very teeny tiny amount of it will dissociate into its component ions, in this case H plus and OH minus. But as you learned from the video, H plus doesn't exist as just a hydrogen ion alone in aqueous solution. It exists as the hydronium ion, H3O plus. All right. So we have that, and we have the hydroxide ion. Okay. Now, I will use the terms hydrogen ion and hydronium ion interchangeably because they effectively are the same thing. Okay. But our textbook exclusively uses hydronium ion, and that's appropriate because, as I said, hydrogen ions don't exist as hydrogen ions in aqueous solution. But you should get used to thinking of them as exactly the same thing. All right, so it's an equilibrium situation, even though only a little bit of it dissociates. But in the context of acid-base chemistry, we're going to see that this is always going to be in play, and this self-ionization of water will always be present in the background of the acid-base chemistry that we do. And because it is an equilibrium, even though it's very, very far to the left, all right, it will behave as an equilibrium behaves via Le Chatelier's principle when we disturb that equilibrium, in this case by adding a bunch of acid or adding a bunch of base. All right, so that in a nutshell is what we're doing in this chapter. So let's talk about acids and bases in a little broader scale here. Scale in this case, looking at the pH scale. So the way we've defined pH, we typically have pH values between 0 and 14. And it can be greater than 14, and it can be less than 0. That really depends on the concentration of the acid or base that we're using. But typically, our concentrations are going to be less than 1 molar. So I'll just remind you of a couple of things from the last time. Let's get our net ionic, well actually, let's just get the equation up here for the self-ionization of water once again. I'll remind you of a few things. So in this case, I'm going to show you the balanced equation with respect to hydronium ion. So H3O plus in aqueous solution plus OH minus in aqueous solution. And in the case of W, which is the equilibrium constant, it's going to be equal to the concentration of the products raised to their stoichiometric coefficients, which in this case is 1. Make this a little smaller. And divided by the concentration of the reactants raised to the power of their stoichiometric coefficients. But I'm not going to put H2O squared in the denominator. And why is that?
It's a liquid.
Because what?
It's a liquid.
Because it's a liquid. But what does that mean? Why do I care if it's a liquid or not? It doesn't change. Why doesn't it change? I'm always answering your answers with another question. Yes?
Because intrinsic properties.
Lots of big words there. Yeah, intrinsic properties, density. That's right. I mean, it's an intrinsic property, meaning that the concentration of water stays the same regardless of the amount of water that we have. Right now, you did it by density. We could also calculate the molarity of water. There actually is a molarity of water. But all of that stays the same regardless of the amount. So we only put in our equilibrium expression the things that are changing in the reaction. So that's it. And we also talked about that when we're at then a case where it's just water, in pure water, there's no other acids, there's no other bases around, we can measure that this concentration is 10 to the minus 7th molar, and this is 10 to the minus 7th molar, which means that K sub W is equal to 10 to the minus 14th. This is just review of what was just on the previous slide, right? But these things you need to reinforce over and over again. Now, when we calculate what pH is, right? pH is equal to the negative log of the hydronium ion concentration So if the hydronium ion concentration in pure water is 10 to the minus 7th, then the pH is 7. And if it's just pure water, we have equal molar amounts of hydronium ion and hydroxide ion. Things are equal. So the pOH would also be equal to 7. And this is what we're defining as neutral pH. Now, why do I put neutral in quotation marks? Well, what is it that's neutral? What's being neutralized?
Charges.
The charges. The charges of what?
Ions.
Ions. So if we look at this, right, there's a positive charge, there's a negative charge. And this reaction, I told you, the equilibrium lies very far to the left. So when hydronium ion combines with hydroxide ion to form liquid water, it's effectively neutralizing the charges. So when nothing else is around and they're equal amounts, things are perfectly neutralized and nothing else is left over. That gives us the pH of 7. That's what we have as neutral pH. So that's drawn here on our scale. Here's our neutral pH. Now, if we have an excess of hydronium ion, let's say we have more hydronium ion. This is when they're equal. So this is when H3O plus is equal to OH minus. How about when they're not equal? How about when hydronium ion concentration is greater than the hydroxide ion concentration? We're still going to have things neutralizing, okay? At the heart of all acid-base chemistry we have the net ionic equation for acid-base neutralization. If you want to know how I got that, you watch the video, okay? The net ionic equation is we have H plus, or hydronium ion, plus OH minus gives us H2O liquid. That's what's happening in all of these. They distill down to the same net ionic equation. There are some complications to it, and you'll see some of them, but in the end, it all boils down to the same net ionic equation. It's the heart of all of this. So that's where we get 1-to-1 molar ratio, okay? When things are completely stoichiometric and everything's equal and there's no hydronium ion or hydroxide ion in excess, things are equalized, we have a neutral pH of 7. But if we do things in a way that gives us more hydrogen ion than we have hydroxide ion, then after the net ionic equation is done, it's not stoichiometric, right? This is 1-to-1-to-1. If we have more hydronium ion than hydroxide ion, then when everything goes to form water, what's left over? Hydronium ion is left over, which means that in that solution, we have more than 10 to the minus 7th molar hydronium ion, okay? There's more hydronium ion left over. So that's going to end up giving us, let's say, I don't know, let's say it's 10 to the minus 6th. Right? It's always going to be 10 to the minus 7. That's always in there. That's in the background. But if we have an excess, now we're adding to that. Maybe it's 5 times 10 to the minus 7th. Or maybe it's 1 times 10 to the minus 6th. Or 3 times 10 to the minus 4th. Whatever. Those are all cases where hydronium ion is more abundant than the hydroxide ion after the net ionic equation is done. Do you all see what I'm talking about there? So that's going to give us an acidic pH, because when we do a log transformation of this, the pH of all that, well, you'd have to plug it all in, but 5 times 10 to the minus 7th, I should have just written any old number down. That's going to be 6.3. How do I know that? I don't have it in my notes, because I can do it in my head. What's the pH equivalent of 1 times 10 to the minus 6? What's the negative log of 1 times 10 to the minus 6? That one you can do in your head. That's 6. 3 times 10 to the minus 4th is going to be 3.3, approximately. But go ahead, use your calculator. Don't use my mind tricks. These are all acidic pHs. Any pH that's less than 7 is going to give you an what we call an acidic pH. Right? The pH is less than 7. And here's some examples. Milk, tomatoes, oranges, vinegar, lemons, all of these things are acids. When you put these in water, they give you an excess of hydronium ion after the neutralization reaction is completed, meaning that the hydroxide ions are limiting and the hydronium ions are in excess. So that's going to give you a lower value for pH. And the opposite is true if we have more hydroxide ions than hydronium ions. If you've added a base, you're going to have an excess of hydroxide ions. That's going to give us what we call a basic pH. The pH is going to be in the basic range. Now this gets a little trickier, right? We started with 10 to the minus 7th when it was neutral. The negative log of 10 to the minus 6th now, right? That's going to be 6. But that's the POH, which means that the pH is equal to 8. So what's the negative log of 3 times 10 to the minus 5th? You can get your calculators out if you want. It should be 4.5. But again, that's the POH. The pH of that is going to be equal to what? 9.5. Did you say 10?
9.5.
I said 9.5. Equals 9.5. Because they add up to 14. pH plus POH is equal to 14. Okay, so everything that we talk about is always expressed in pH. So you have to remember that pH reflects the hydrogen ion concentration. It's straightforward when you're working with acids. But if you're working with a base, you just calculate the POH, and then you have to subtract that from 14. It's something you got to keep your eyes on and remember when you're doing these things. Here's a couple of examples of bases. Sodium hydroxide you're very familiar with as a base. But drain cleaner is very basic. Household ammonia, milk of magnesia. We'll be doing a lab with milk of magnesia. It's pretty fun later on. Now, something else to keep in mind, all right, because these are negative log transformations and the numbers are less than 1. So it kind of goes counterintuitive. Let me show you what I mean by that. If I take the hydronium ion concentration, and let's start with, say, 0.01 molar, which is the same as 10 to the minus 2nd molar, right? And let's just make that more and more dilute. And I'll just go down by factors of 10. So as I get more dilute, 0.001 molar, that's 10 to the minus 3rd molar. 0.0001 molar, that's 10 to the minus 4th molar. 0.00001 molar, which is 10 to the minus 5th molar. Okay? What does that do to the pH that we would measure? Right? The pH, which is negative log of the hydronium ion concentration. So I made all these easy for you. What's the negative log of 10 to the minus 2nd? 2. Negative log of 10 to the minus 3rd is 3, 4, 5. It's becoming less acidic. As this becomes less acidic, that also means it's becoming more basic. But as this becomes less acidic, pH value increases. That's what I mean by counterintuitive. Something's getting smaller and smaller, but the pH value is increasing. That's simply because it's a negative log transformation. The other thing to notice is that here we have a jump from 2 to 3, or a jump from 2 to 4, but that's a 10-fold, a 100-fold, a 1,000-fold jump, right? This is a 10x jump. This is a 100x jump. This is a 1,000x. So every one increase in pH unit is really a 10-fold change in the concentration. So that's another thing to remember. One pH unit is equal to a 10-fold change in concentration. Okay? So really all this slide was a lot of more definitions of the same general ideas. I just showed you some examples of them at all. But the main concepts here, I'll just talk about them and highlight them. The main concepts here, right? The heart of all acid-base, we need a better color than that. The heart of all acid-base reactions are going to be the net ionic equation. Right? When we have this situation, we're at neutral pH. You need to understand neutral pH versus an acidic pH versus a basic pH. And you need to understand this counterintuitive nature of what pH actually represents. Okay? Now, I promised you we're going to talk about titrations today to set you up for the lab. So let's go ahead and do that. Let me start by just saying that the titration itself is just a technique. In fact, it's a quantitative technique. And it allows you to determine the concentration of an acid using a known concentration of base, or vice versa. Do I need to write that out for you? Do I need to spell that out? Yes, I heard somebody say yes. You really want to write this? Okay, let's put it down here. It's a quantitative. Should have just put this as a bullet on the slide. Technique to determine the concentration of an unknown acid or base using a standard known of the other. Well, I really should have had that on the slide for you ahead of time. I don't know, some would say the act of writing it down makes it stick in your head more than just, oh yeah, it's on the slide, I can read that anytime. All right, so that's the technique. But really, the experiment itself, it's just a neutralization reaction. Same neutralization reaction that I talk about in the video that gives you the net ionic equation. You can also think of this as a double replacement reaction if you want to, okay? But at the heart of all of this, the heart of any neutralization reaction, okay, let me get this out of the way. You've got basic components. You've got an acid, and you mix the acid with the base, and you'll always get a salt of the acid, and you'll get water. Those are the common components of an acid-base neutralization reaction. And what's at the heart of this acid-base neutralization reaction? H3O plus in aqueous solution plus OH minus in aqueous solution will come together to form H2O liquid. And when everything is stoichiometric, everything is stoichiometric and neutralized, then we will have this situation. The hydronium ion concentration will be equal to the hydroxide ion concentration. And when that's the case, what will the pH be? It will be 7, right? This pH will always be 7 when the hydronium ion concentration is equal to the hydroxide ion concentration. Now, on Friday's lecture, we talked about strong acids and bases and weak acids and bases. Did we not? I don't remember, actually. We did. Okay. So let's just worry about strong. Those are the easiest ones to deal with. And tomorrow's lab is just going to be using strong acids and strong bases. Where it becomes complicated is when we use weak acids and bases, because those are in equilibrium, all right? So it gets a little bit more complicated, and we'll get there, but not today, all right? So let's just deal with a strong acid. Now, what does it mean again to be strong? It completely dissociates, or virtually 100%, okay? So virtually 100% dissociation. So in this case, we have hydrochloric acid. So let's put that in there. HCl in aqueous solution is going to dissociate virtually 100%. Now, I'm going to actually put this in the context of hydronium ion. So for my reaction to be balanced, I need to have a mole of H2O liquid here, okay? And when the HCl dissociates 100%, I'm going to get 1 mole of H3O plus in aqueous solution and 1 mole of chloride ions in aqueous solution, right? Now, I'm going to treat this like a rice table, except it's not an equilibrium expression. This goes to completion. So instead of a rice table, I'm just going to say, well, initially, what do we have initially? Before things dissociate, we're going to have some concentration of HCl. We're not told what it is, so I'm just going to put a box. There's some molar concentration of HCl that we're starting with. And initially, there's 0 molar hydronium ion and 0 molar chloride ion. And then we don't need to worry about the change and the equilibrium. We can just say, well, what's going to happen at the end? Because we know this reaction goes to completion. We're told it's a strong acid. So in the end, it doesn't matter what was in the box because 0 is left, all right? And whatever was in the box, we're going to have, since this is 1-to-1 for this acid, we're going to have that molarity of hydronium ion and that molarity of the chloride ion. But just to make sure you've been following along, why didn't I put anything here under H2O? Because it doesn't change. It's in liquid. So we're not concerned. Nothing's changing. Initial, final, it's the same. So let's just put a line. We don't need that. So whatever we start with, whatever concentration we start with, all of that goes into the hydronium ion concentration. So whatever this is, okay, all goes into the hydronium ion concentration. So we know what the hydronium ion concentration is, therefore we can calculate the pH. Yeah.
What if you don't have enough water?
What if you don't have enough water for the hydrogen ion to attach to the H2O to form hydronium ion? That's a good question. Acid-base chemistry really, in the context that we're discussing, is dilute acids and bases in water. So even though you may be adding concentrated acids and concentrated bases, you're doing it in a volume of water that overall they're going to be dilute, because the numbers, look at the molarities that we're working with, all right? The molarities are really, really small. So in your situation, which I suppose could happen, that's basically water is no longer the solvent. If you want to get back to solutions and solutes and solvents, that wouldn't be written as HCl in aqueous solution anymore, because now HCl is the solvent if there's not enough water around. So simple answer is it won't apply, but it's a good question. Okay, and we can say the same thing for a base, right? If I take, what's the base here? Sodium hydroxide. Whatever amount of sodium hydroxide we start with, all of it is going to end up as sodium ions in aqueous solution and hydroxide ions in aqueous solution. And all of the NaOH that we start with ends up as OH minus ions in aqueous solution. So in other words, if I know that this reaction's balanced, and it is, right, this is 1 to 1 to 1 to 1. So I know that if I add the same molarity of HCl and the same molarity of NaOH, I'm saying the same for both of them, then I'm going to have the same concentration of hydrogen ions as I have as hydroxide ions, and I'm going to have a neutral pH. If everything is stoichiometric. Okay? Now, the way we actually do this, the titration experiment itself, we have a pH meter that in lab you're going to use. It's a digital readout. They don't work very well. I'm warning you now. And we're going to plot pH on the y-axis. Yeah, you're going to make a graph. You're going to make two of them. And in that experiment, you're going to figure out the concentration of a strong acid. And you're going to do it by adding a strong base until you get to this magic place where things are equal. Because when things are equal, when we get to this magic place, what do we know about the pH? It equals 7. Okay? And you can see it right here. Here's pH 7. And look what happens at pH 7. We are at what we call the equivalence point. This is the kind of curve that comes from doing a titration experiment. So you start with all acid and no base. See, the volume of base that you've added here is 0. So this is all acid. So at the very beginning, all you have there is acid, so you would expect there to be an acidic pH. There it is. It's about 1, let's say. So right now, you could probably read right off of there and say, okay, I know what the concentration of this is because it reads a pH of 1. I know that that's 1 times 10 to the minus first molar. But our pH meters aren't that good, okay? So you can't tell that. Let me write that 1 a little better. It doesn't matter what it is. That's the initial. But as we add more and more sodium hydroxide, right, it starts to rise up a little bit, but this net ionic equation is constantly happening. I don't have it written up here. Yeah, here it is. This is always happening. We're starting with 100% this, and we're slowly adding hydroxide ions. And we know how much we're adding because we know the volume of NaOH, and we know that every volume of NaOH, every little bit that we put in, it all goes to, where to go? It all goes to hydroxide ion concentration. Okay? So all we want to do is note very carefully how much sodium hydroxide does it take to add to get to this magic equivalence point. That's really all we're doing in a titration experiment. If we go beyond, if we add too much sodium hydroxide, now we have this situation where the net ionic equation is all done, and now we have an excess of hydroxide ions because I've added too much sodium hydroxide. So what's that going to do to the pH? It's going to make it go even higher. And that's exactly what happens. Here's the equivalence point. This is where everything is equal. All right, pH is equal to 7. And let me, if you weren't clear on this, let me emphasize that at the equivalence point, what's equal? The hydronium ion concentration is equal to the hydroxide ion concentration. That's what's equal at the equivalence point. Once you understand the technique, then you use the stoichiometry of the net ionic equation, you can solve any of these problems. So in a typical experiment now, we're going to take, what are we going to take? We measure out 25.35 milliliters of HCl. So that's what's right in here. Oh, that says acetic acid. Well, it's supposed to say HCl. Please fix that in your slides. And we want to know what the concentration of that is. So we're going to titrate it with 0.1200 molar NaOH. And when we do our experiment and we plot it out and we can figure out what volume does it take to get to the equivalence point. That's what this is. This is the volume to get to the equivalence point. And we're going to use that to figure out what was the concentration of the acid that we're titrating. Now this math is no different from all of the stoichiometry math that hopefully you remember doing in Gen Chem 1. Probably don't remember that, so let's just go over it step by step. Let's figure out, we know the heart of all of this is what? H3O plus OH minus goes to H2O. We know that that's happening in this reaction. So if we can figure out how much hydroxide ion is in there, then we'll know how much hydronium ion is in there. And if we know that, we know what volume it's in, we can get the molarity. It's that simple. So let's start with 35.15 milliliters of this NaOH. But before I do any more, okay, what's the units of molarity? Moles per liter. This is in milliliters. So I don't want to be working in milliliters. I want to be working in liters. So you can do that transformation in your head, or you can write it out. That's fine. That's the same as 0.03515 liters. Okay? Liters of what? Well, it's liters of 0.1200 molar NaOH. That's moles per liter. So I want liters on the denominator. 0.1200 moles of NaOH per liter. That's the molarity. Now that gives me how many moles of NaOH? Well, we got to calculate it. 0.03515 times 0.1200 gives me 0.004218 moles of sodium hydroxide. That's how many moles I added from the burette into the vessel to get to the equivalence point. Now we know this is a strong base. So that tells us how many moles of sodium hydroxide there were, right? We know it's strong. So for every mole of NaOH that I add, I'm going to get the same number of moles of hydroxide ions, right? So that means I'm going to have 0.004218 moles of hydroxide ion, right? And I know my net ionic equation. That's going to react 1-to-1 with hydronium ion concentration. Because H3O plus OH minus react 1-to-1 to give me H2O liquid. So that means I'm going to have 0.004218 moles of hydronium ion that were neutralized. Now, where does the hydronium ion come from in this experiment?
HCl.
Coming from HCl. And I know that HCl dissociates into hydronium ion plus chloride ion, 1-to-1. So if I know how much hydronium ion was there, I know how much HCl produced it. That's moles of HCl, and what's the volume? The volume is right here, 25.35 milliliters. That contained this many moles. So let's divide this by 0.02535 liters, and I'll have the molarity of HCl equals 0.166 molar HCl. Now that's just showing you the individual steps, talking about them. I can show you the same thing by dimensional analysis. In fact, let me do that. Let me just shrink this up a little bit. Give myself a little bit more room. We can lay the whole thing out by dimensional analysis here. We can start with 0.03515 liters, and that's of NaOH solution. The concentration of that solution was 0.1200 moles of NaOH per liter. And I'll just be formal. I'll show every single term here. I know that for every 1 mole of NaOH, we produce 1 mole of OH minus. Okay? And I know that every 1 mole of OH minus reacts with 1 mole of H plus. Okay? And I know that there's 1 mole of H plus produced from every 1 mole of HCl. That will also give me moles of HCl. It's just all lined up. It's a bunch of ones. And that's the math. It's no different from the math you've done before. Titration, it just uses that math, but it does so generating the data from instruments that are more sensitive than what you're used to using. In this case, using the burettes that are sensitive down to 2 decimal places per milliliter. So it gives us a little bit more sensitivity. The only other spin on this math is when you don't have an acid or a base that produces 1 hydrogen ion in solution or 1 hydroxide ion in solution. For example, let's say we did the same experiment, but now we used barium hydroxide as our base instead of sodium hydroxide. So now, every 1 mole of barium hydroxide, how many moles of hydroxide ion does that produce in solution? 2. 2 moles of hydroxide ion, right? And that term is going to go right here. It's not 1-to-1 anymore. It's 2-to-1. Or what if we used, here, what if we used a different acid? Here's phosphoric acid. Right, we haven't talked about these things yet when you have more than 1 hydrogen ion or more than 1 hydroxide ion that's produced. Those are called polyproduct or polybasic acids and bases. But you can tell there's H3. So for every 1 mole of phosphoric acid, how many moles of hydrogen ion can be produced? 3. And that term would go here. Let's go back to what we were learning about the net ionic equation for the neutralization reaction and how we express that as an equilibrium and then take a negative log transformation of that to give us easily to manage numbers, all right, which we call pH and pOH. And let's just use them to practice a little bit about how we can solve simple and then, as we get there, more complicated pH problems. So here's a classic one, number one. Calculate the pH of a 0.001 molar aqueous solution of, anyone know what this is called? We haven't talked about the names of these acids yet. Anyone happen to recognize this one? Nitric acid. Okay, so I'll start you off slowly. We want to know what the pH is. The pH is a numerical representation of the concentration of hydrogen ions that are in solution, otherwise known as hydronium ions. So we're going to use this equation. pH is equal to the negative log of the concentration of hydronium ions. Now, what is the concentration of hydronium ions? Now, you need to be told something that's not in this problem, and I haven't lectured to you about it yet, although we did talk about strong and weak electrolytes and strong and weak acids and bases at the very beginning. All right, this is a strong acid, so I'm telling you now, nitric acid is a strong acid. But what does that mean to you if I tell you nitric acid is a strong acid? Yeah, it completely dissociates, or it virtually it dissociates virtually 100%, almost 100%, as if it were 100%. Okay, so we're going to write this equation then as, here's nitric acid, HNO3 in aqueous solution, will dissociate virtually 100%. So it's not in equilibrium. I'm going to draw an arrow that goes to the right, even though it really is in equilibrium. It's just the equilibrium lies far, far, far to the product side. Okay, that's going to give us the products. And what are the products? Hydrogen plus, which is really the hydronium ion, plus the nitrate ion. 100%. So if I say this is my initial conditions. The initial conditions is I'm going to start with 0.001. And I'm going to put that in scientific notation. Okay? 1 times 10 to the minus third molar. Which is really the same as just saying it's 10 to the minus third molar, right? So I'm going to simplify it even more. Now, initially, before anything happens, we have nothing's dissociated yet. It's 0 molar, 0 molar. But because it dissociates 100%, we don't need to build a full rice table for this. We can just identify what's going to happen at the end. It's going to be 0. All of it's dissociated. So this is 0 molar, and we have 10 to the minus third molar of one product and 10 to the minus third molar of the other, because they dissociate in a 1-to-1 ratio. We can tell that from the stoichiometry of the balanced equation. So all we care about then is identifying the pH. Now we know the concentration of hydrogen ions in solution. It's 10 to the minus third. So this becomes pH is equal to the negative log of 10 to the minus third. Now you can use your calculator if you want to, but if you understand how logs work, and in this case log base 10, what's the answer? It's 3. Right? Because we're taking, it's just, there's no coefficient, it's just the exponent. And because it's a negative log, if we're the log of 10 to the minus third, it would be minus 3. Let's do the same thing for an aqueous solution of sodium hydroxide. And I'll tell you, this is a strong base. So let's write that out. Sodium hydroxide in aqueous solution dissociates virtually 100% into sodium ions in aqueous solution plus hydroxide ions in aqueous solution. So if I start with, initially, if I start with 5 times 10 to the minus fourth molar sodium hydroxide, and there's nothing over here, what am I going to end up with? 0 molar of sodium hydroxide and all of it's dissociated, and it dissociates 1 to 1. So the concentration of sodium ions is what? 5 times 10 to the minus 4th molar. And what's the concentration of hydroxide ions? 5 times 10 to the minus 4th molar. So, what's the pH? You might need your calculator for this one. If you can't do negative log transformations in your head.
3.3.
3.3. So what's the pH?
10.7.
10.7. The pH is not 3.3. Why isn't the pH 3.3? Because we calculated the pOH, right? Because this is a base. So I didn't tell you what it was. I just said it's the negative log of that. That's the pOH, which means the pH is going to be equal to 14 minus 3.3, which equals 10.7. That's probably one of the most common mistakes students make when they do these simple pH questions. Is they're working with a base, and they do all this math, and they do the negative log transformation, and they say that's the pH, not recognizing that they're working with a base. So what you've actually calculated is the pOH, so you got to subtract that from 14. So what I usually say after I tell you that this is the most common mistake that students make, don't be that student, okay? Don't make that mistake. So now we're going to put some sodium oxide into water. Now you don't know yet, we haven't had this discussion, how to identify what's an acid and what's a base. Although I think I might have mentioned it in passing in the video. Right? If you have a metal 1 or metal 2 oxide, or a metal 1 or metal 2 hydroxide, that will be a strong base. I'm not going to write that down now because there's no room, and we'll talk about that in a slide or two. Okay. So this is a group 1 oxide, sodium oxide. This is going to be a strong base. Now, how would we write a reaction that describes how that strong base reacts? Well, let's put that base in water. So here's H2O, H2O liquid, plus sodium oxide. We put that in aqueous solution, and let's just do, well, it might not be obvious because we're going to split up the water. Now, the water, if you remember from the video, water can behave as both an acid and a base, depending on what it's doing in the reaction. Anyone remember the special word for that? It starts with an A. Amphoteric. That's right. That's the special word where water, or anything that's amphoteric can behave as a Bronsted-Lowry acid and a Bronsted-Lowry base. So what's happening here is sodium oxide, that's behaving like a base. All right? The actual thing that's behaving like a base is the oxide ion itself. And let me show that to you, all right? Because this is an ionic compound, right? Sodium is 1 plus cation, and oxide is a 2 minus oxide ion. So let me show you that oxide ion. There it is in the Lewis symbol, right? So oxygen's acquired 2 more electrons to become isoelectronic with its nearest noble gas. Remember all that stuff from Gen Chem 1? That's why we learned all that, okay? So there's the oxide ion, and it's going to react with water. So let me draw some water here. Here's a Lewis structure for water, all right? And we know that those are polar bonds, so that there's a dipole moment, and there's a delta positive end by the hydrogens, and a delta negative end by the oxygens, because the oxygens are more electronegative. Is it all coming back to you now? But the electrons are negatively charged, right? We can show that on that oxygen-hydrogen bond, the hydrogen side is really, really positive. Well, I might call that electropositive versus electronegative. So what's going to happen is these electrons are going to be attracted to the positively charged hydrogen, almost. It's almost a hydrogen ion, H+, but it's not quite. It's still bonded to the oxygen here, so it's still a covalent bond. But when these become in proximity, these electrons are going to come over here, grab that hydrogen, and now it's going to form a covalent bond. So what this is going to give us then is one hydroxide ion, which if I put all the electrons in, sure, what the heck, might as well, right? I have to show that then formally. Let's put a bracket around them. This is overall negatively charged. And then what's left on that water? The water now lost that hydrogen, so that water, I'll keep that in blue, looks exactly the same. We formed two hydroxide ions now. So the oxide is acting like a base. It's accepting a proton, and the water is acting like an acid. It's donating a proton. You'll see how that works? So what we have then, what's left over here is sodium ions and hydroxide ions. That's what we're making in the end here. But we have to balance this, all right? We have 2 sodium and we have 2 hydroxides. And of course, these are in aqueous solution. So that was just a little side conversation, but to show you how sodium oxide actually behaves like a base when it's in aqueous solution. And the sodium has nothing to do with it. The sodium's actually not involved. The sodium is a spectator in all of this. If I were to write out the full ionic equation and show it to you, but we're not going to do that. Let's get back to the task of this problem. So our initial concentration now is of 0.005 molar sodium oxide, and initially we have none of this. It hasn't happened yet. When we're done, this goes to 0, and really, well, it's 2 to 2, right? We had 1 mole of sodium oxide dissociating into 2 moles of sodium and 2 moles of hydroxide ion from this equation. So what is the concentration of sodium ions here? So what? 0.01. It's 0.01. You all see that? This is really important, folks. We went from 0.005 to 0.01. Why? Why? Because of the coefficients. 1 mole dissociates into 2 moles and 2 moles. So you follow the coefficients to inform you of how these concentrations are changing. Just like you learned how to do when we built rice tables. And we were doing this with equilibrium. And we'll be doing that again. Don't forget all those skills. All right, a lot to keep in mind. So ultimately now, all this work to get us here. You either want to get to the concentration of hydroxide ions if you're working with a base, through which then you can calculate the pOH and then subtract that from 14 and get the pH. Or you're working with an acid and your whole goal is to get to the concentration of hydrogen ions. If you have that, you have the pH. So this gives us the pOH, and what is the pOH? Say it louder.
2.
Say it strong.
2.
2. That's right. So what's the pH?
12.
12. What are the hydronium ion concentrations and the hydroxide concentrations of ammonia if we're given the pH is 11.7? We use the same equations. You're going to need to take antilogs here. You want to try working on this? Yeah. Got it? Okay. Let's check our work, because there's a number of ways you can do this. All right? I'll show you one way, and then hopefully we'll come around and solve it all ways. So first, let's do it with antilogs, because that's what we just learned how to do. So you're given the pH. So we know how to get what the hydronium ion concentration is directly by just taking the antilog of that, right? 10 to the minus pH, that's going to be equal to the hydronium ion concentration. So that's going to be 10 to the negative 11.7. What does that equal? 2 times 10 to the negative 12. Okay. Now, we've got a couple different ways that we can calculate the POH. One way, actually, why don't you guys tell me? How did you do it? Let's see. Should I pick on one of you, or does somebody want to? So that's going to be, you said that's the POH, right?
Yes.
Now we do the same thing. We can take the antilog of that, and we'll get what the hydroxide ion concentration is. Equals 10 to the negative POH, which we just did from 14. That's 10 to the negative 2.3. And what does that equal? 5 times 10 to the negative 3, right? Okay. So this should be correct. Now, how might we check that? Okay, how can you check to see if that's right? What else do you know about how these things behave that would allow you to see if that's correct? Multiply them together, because what does that tell you?
It should add up to 14 if it's right.
Because of this, right? The concentration of the hydronium ion times the concentration of hydroxide ion should equal to the ion product constant of water. And it does, all right? If you multiply these two together, you're going to get, and you can do this one in your head, or you can use your calculator. Please use your calculator, all right? But 2 times 5 is 10, and 10 to the minus 12th times 10 to the minus 13th. There you add the exponents, so that's 10 to the minus 15. And that's the same as 1 times 10 to the minus 14. So that's a good check that you've done things correctly. Now, as I said, there's other ways you can do this. So we could have done this instead. Once we calculated the hydronium ion concentration first. So you could have also done this. 2 times 10 to the minus 12 times x is going to be equal to 1 times 10 to the minus 14, because that's the ion product constant of water. And then you just solve for x. X is equal to 1 times 10 to the minus 14 divided by 2 times 10 to the minus 12. Equals. And you plug that in your calculator, you should get 5 times 10 to the minus 3. And you will. I mean, what's 1/2? 1/2 is 0.5. And when you divide exponents, 10 to the minus 14 divided by 10 to the minus 12, you subtract them. So that's times 10 to the minus second. All right, and now using that same trick, right? That's the same as 5 times 10 to the minus third. We have to make this bigger by 10, so we make that smaller by 10. So we've already defined strong. It's virtually complete, the dissociation. Now on this slide, I have a double-headed equilibrium arrow. Maybe that's by mistake, I don't know. But let's emphasize that really the equilibrium, because really, these reactions don't go completely to the right. They are at equilibrium, but the equilibrium falls so far to the right, I'm just going to emphasize that this way. Okay? And we know how, if it's in equilibrium, we know how to write the equilibrium expression for this, KEQ. KEQ is equal to the concentration of the products raised to their stoichiometric coefficients, which is 1 in this case. A minus is just whatever's left over here. HA is a generic acid. There's the hydrogen that pops off, and the A minus is what's ever left over. All right, so that's the products divided by what? But what? What's in the denominator?
HA.
HA.
That's all.
That's all? What about the H2O?
It's not gonna equal.
No, I want to put it in because we put everything in, don't we? Why not? The liquid. But what does that mean? It's a liquid. It does. The concentration doesn't change. We only put in the things where the concentration changes. Now that's the equilibrium expression. And because it's an acid, we're going to call this the Ka, right? We did that on Monday as well. But Ka, it's just the equilibrium constant. Now here is a list of the 6 strong acids. There's only 6 of them that you need to worry about. In fact, I think there's really only 6 that we classify as being strong. So you could just memorize them. Hydrochloric acid, HCl, hydrobromic acid, HBr, hydrobiotic acid, HI, and then you've got perchloric acid, HClO4, and then sulfuric, which you're familiar with, H2SO4, and nitric, which I told you about, HNO3. Those are the only 6 that you have to remember. There's the equilibrium expression, the reactions written out for you, okay? And if you look at the Ka, the Kas aren't listed? Yeah, they are, right here. Look at the Kas. Even though they're strong, we still have a Ka. They're just huge. 10 to the 6th, 10 to the 9th, 10 to the 9th, 10 to the 10th. Now, even 10 to the 3rd. Now, and even nitric, 10 to the 1st. You think of nitric acid as being, it's so scary. It's like the worst there is. Or sulfuric, it's the worst there is. But look, it's not so tough. It's not so tough. It's only 10 to the 3rd. If you look at this, 10 to the 3rd compared to perchloric. Okay. It's not so much whether it's strong or weak. It's the concentration of the acid that makes it dangerous. Okay. Ka just talks about the extent of dissociation. You need to know what the concentration is to know if it's really going to hurt you. All right? I don't know if I can emphasize that enough. But all of these are classified as strong, virtually 100%. Even though even nitric acid, the Ka is only 24. So you still do have some reactants left at equilibrium. But before we get into that conversation, or maybe we'll just leave that for Friday, I want to tell you a little bit more about the bases. All right, the strong bases. And what I told you earlier, okay, any group 1 or group 2 metal hydroxide or metal oxide will behave like a base, a strong base. And the generic equation that we would have for that, all right, we'll use B for our base, okay, some B that has an OH in aqueous solution will be in equilibrium, but really it's going to be virtually 100%. When it loses the hydroxide ion, it's going to be B plus in aqueous solution plus OH minus. Now that's the definition of an Arrhenius base. I've been talking about Bronsted-Lowry bases. Definition of an Arrhenius acid is it produces hydrogen ions in solution, and an Arrhenius base produces hydroxide ions in solution. Okay. The reason I'm using that as an example here is because it is a group 1, group 2 metal hydroxide. So it has a hydroxide. So these include things like, well, everything that's listed here. Sodium hydroxide, lithium hydroxide, potassium, calcium, barium, strontium. These are all group 1 or group 2 metal hydroxides. Here's their chemical formula. Here's the equation that describes their dissociation. These all have, if it were listed here, these all have K sub B's that are much larger than 1. It's the same definition as for a strong acid. And the same is true for the group 1 and group 2 metal oxides. So oxides and hydroxides. And I already showed that to you for the oxides in the earlier example, right? If I show the metal as an M, all right, so if it's MO, is that a group 1 or a group 2 metal? Group 2, right? Because the charges have to cancel for it to be a neutral. This is drawn as a neutral. So this is group 2 and this is group 1. So this would be things like magnesium oxide, right? Or calcium oxide. Group 1, well, I showed you one example of that, right? Sodium oxide or lithium oxide. Now, the generic equation I would describe for that, here's your base, there's your metal oxide, and we put that in water, and just like I showed you before, it's going to form hydroxide ions in solution, okay? It's going to make the solution basic. So here, now I'm showing you a Bronsted-Lowry definition of a base. It's accepting a proton from solution, and that proton came from the water. So there's what's left over. Now you might say, wait a minute, why isn't that Arrhenius? Because we produced hydroxide ion. But this hydroxide ion is not coming from the base. It's coming from the water. It's left over because water was acting like an acid to donate the hydrogen.